fully rated system is designed to handle the maximum available fault current at the point of common coupling, while a series rated system is designed to interrupt a specific level of fault current that is less than the maximum available fault current. Practically speaking, there are differences for installers. For fully rated systems, the equipment will require higher interrupting ratings to handle the maximum fault current. Series-rated systems may use equipment with lower interrupting ratings, as the series devices limit the fault current to a low level. Installation-wise, fully rated systems typically require higher gauge conductors and larger breakers or fuses to carry and interrupt the maximum fault current. Series-rated systems may allow for smaller gauge conductors and smaller breakers or fuses, as the series devices limit the fault current. Series-rated systems incorporate devices that limit the fault current to the specified level, one of which is current-limiting fuses, which interrupt the circuit with a rapid time current characteristic, limiting the fault current to a predetermined level. The other is current-limiting circuit breakers, which automatically trip with a time current characteristic that limits the fault current to a specified value. There are other considerations. In series-rated systems, the series devices must be properly coordinated with other protective devices in the system to ensure proper operation during a fault. Series-rated systems may require specific testing procedures to verify the correct operation of the series devices. Series devices may require periodic maintenance or replacement to ensure their proper functionality. The primary difference between fully rated and series-rated systems lies in the ability of the system to interrupt fault currents. Fully rated systems are designed for the highest possible fault current, requiring higher rated equipment and thicker conductors. Series-rated systems use series devices to limit fault current, allowing for low-rated equipment and potentially smaller conductors. However, series devices require coordination, testing, and maintenance to ensure proper operation. When evaluating an electrical system design, one of the most critical factors to consider is its ability to handle fault current. Fault current is the excessive electrical current that flows during a short circuit or other electrical fault. If not properly managed, fault currents can cause significant damage to equipment, pose safety hazards, and even lead to fires. Two primary approaches to designing electrical systems to handle fault currents are fully rated systems and series-rated systems. In a fully rated system, all components, including circuit breakers, fuses, and conductors, are selected and rated to withstand the maximum available fault current at their location in the system. This means that each component must be capable of interrupting or withstanding the full magnitude of the fault current without failing or causing damage. Fully rated systems offer a high degree of protection and reliability, as they are designed to handle the worst-case fault scenarios. However, they can also be more expensive to implement, as they require high-rated and often larger equipment. In contrast, a series-rated system uses a combination of components with different interrupting ratings to achieve the desired level of fault current protection. In a series-rated system, the upstream components, such as the main circuit breaker or fuses, have a higher interrupting rating than the downstream components, such as branch circuit breakers or fuses. The upstream components are designed to limit the fault current to a level that the downstream components can safely interrupt. Series-rated systems can be more cost-effective than fully rated systems, as they allow for the use of lower-rated and often smaller equipment in certain parts of the system. However, they also require careful coordination and selection of components to ensure that the upstream devices will properly limit the fault current before the downstream devices are subjected to excessive stress. One of the key differences between fully rated and series-rated systems lies in the selection of equipment. In a fully rated system, all circuit breakers, fuses, and other protective devices must have an interrupting rating equal to or greater than the maximum available fault current at their location. This typically requires the use of higher rated and more expensive equipment. In a series-rated system, the downstream circuit breakers or fuses can have a lower interrupting rating than the maximum available fault current, as long as the upstream devices are capable of limiting the fault current to a level that the downstream devices can safely interrupt. This can result in significant cost savings, as lower-rated equipment is generally less expensive. The installation requirements for fully rated and series-rated systems also differ. In a fully rated system, the conductors must be sized to carry the maximum available fault current without overheating or causing excessive voltage drop. This typically requires the use of larger gauge conductors, which can add to the cost of the installation. In a series-rated system, the conductors can be sized based on the normal operating current of the circuit, as the upstream devices will limit the fault current to a safe level. This can allow for the use of smaller gauge conductors, which can reduce the cost of the installation. Coordination is a critical aspect of series-rated systems. The upstream and downstream protective devices must be carefully coordinated to ensure that the upstream devices will trip before the downstream devices are subjected to excessive fault current. This coordination is typically achieved through the use of time current curves, which plot the tripping time of the devices against the magnitude of the fault current. The time current curves must be carefully analyzed to ensure that the upstream devices will trip quickly enough to protect the downstream devices. Testing is also an important consideration for series-rated systems. After the installation is complete, the system should be tested to verify that the upstream devices are properly limiting the fault current and that the downstream devices are capable of safely interrupting the limited fault current. This testing typically involves injecting a simulated fault current into the system and measuring the current and voltage at various points. Maintenance is another factor to consider when comparing fully rated and series-rated systems. Fully rated systems generally require less maintenance, as all of the components are designed to withstand the maximum available fault current. Series-rated systems may require more frequent maintenance, as the upstream devices are subjected to higher levels of stress during fault conditions. The devices should be periodically inspected and tested to ensure that they are still functioning properly. Several types of devices can be used to limit fault current in series-rated systems. Current-limiting fuses are one common type of device. These fuses are designed to interrupt the circuit very quickly when a fault current occurs, limiting the magnitude and duration of the fault current. Current-limiting circuit breakers are another type of device that can be used to limit fault current. These circuit breakers use special mechanisms to quickly interrupt the circuit when a fault current occurs. Other devices, such as reactors and impedance transformers, can also be used to limit fault current in series-rated systems. Reactors are inductors that are placed in the circuit to add impedance, which reduces the magnitude of the fault current. Impedance transformers are transformers that are designed to have a high impedance, which also limits the fault current. When designing an electrical system, it is important to consider the available fault current at various points in the system. The available fault current is the maximum amount of current that could flow during a short circuit or other electrical fault. The available fault current can be calculated using various methods, such as the point-to-point method or the infinite bus method. The calculated available fault current is then used to select the appropriate interrupting ratings for the circuit breakers and fuses in the system. The National Electrical Code, or NEC, provides guidelines for designing and installing electrical systems. The NEC covers various aspects of fault current protection, including the selection of interrupting ratings for circuit breakers and fuses, the coordination of protective devices, and the testing of series-rated systems. The NEC also includes tables and examples that can be used to calculate available fault current and select appropriate protective devices. Selecting between fully rated and series-rated systems involves weighing the trade-offs between cost, performance, and reliability. Fully rated systems offer a high degree of protection and reliability, but they can be more expensive to implement. Series-rated systems can be more cost-effective, but they require careful coordination, testing, and maintenance to ensure that they will function properly during a fault. Ultimately, the best choice depends on the specific requirements of the application. For critical applications where reliability is paramount, a fully rated system may be the best choice. For less critical applications where cost is a major concern, a series-rated system may be acceptable. Understanding the available fault current is paramount in electrical system design and safety. Fault current is the amount of electrical current that flows during a short circuit. If the electrical system cannot handle the fault current, major equipment damage, fire, or shock and electrocution can occur. Electrical distribution systems should be engineered with proper overcurrent protection devices to protect the conductors and equipment. Fault current is the electrical current that flows through a circuit when a short circuit condition exists. A short circuit occurs when there is an unintentional low resistance path for current to flow, bypassing the intended circuit pathway. This can happen due to insulation failure, accidental contact between conductors, or equipment malfunction. During a short circuit, the current can increase dramatically, often reaching thousands of amps in a fraction of a second. These high fault currents can generate significant heat, which can damage equipment, melt conductors, and ignite fires. Available fault current is the maximum amount of fault current that an electrical system can deliver at a specific point in the system. It is determined by the characteristics of the power source, such as the utility transformer or generator, and the impedance of the circuit. Impedance is the opposition to the flow of alternating current and includes resistance, inductance, and capacitance. The lower the impedance, the higher the available fault current. The available fault current is highest at the service entrance, where the electrical system connects to the utility power source. It decreases as you move further downstream in the system due to the impedance of the conductors, transformers, and other equipment. Calculating available fault current is essential for selecting the appropriate overcurrent protection devices. The interrupting rating of an overcurrent protection device, such as a circuit breaker or fuse, is the maximum fault current that the device can safely interrupt without failing or causing damage. The interrupting rating of the overcurrent protection device must be equal to or greater than the available fault current at its location in the electrical system. If the interrupting rating is too low, the device may fail to interrupt the fault current, leading to equipment damage and potential safety hazards. There are several methods for calculating available fault current. The simplest method is the point-to-point method, which calculates the available fault current at each point in the system based on the impedance of the upstream component. The point-to-point method is generally accurate for simple systems with few branches. For more complex systems, computer software programs are often used to perform fault current calculations. These programs can accurately model the electrical system and calculate the available fault current at various points. Electrical codes and standards, such as the National Electrical Code, provide guidelines for calculating available fault current and selecting overcurrent protection devices. These codes and standards also require that electrical systems be labeled with the available fault current at the service entrance. This information is essential for ensuring that the electrical system is properly protected against fault currents. Overcurrent protection devices are designed to protect electrical systems from overcurrents, including fault currents. These devices include circuit breakers, fuses, and ground fault circuit interrupters. Circuit breakers are electromechanical devices that automatically trip and interrupt the circuit when an overcurrent is detected. Fuses are one-time devices that melt and break the circuit when an overcurrent occurs. Ground fault circuit interrupters are designed to protect people from electric shock by detecting ground faults and quickly interrupting the circuit. The selection of overcurrent protection devices should be based on the available fault current, the conductor ampacity, and the type of equipment being protected. The interrupting rating of the overcurrent protection device must be equal to or greater than the available fault current at its location in the electrical system. The conductor ampacity is the maximum current that the conductor can safely carry without overheating. The overcurrent protection device should be sized to protect the conductor from overloads and short circuits. Electrical systems can be designed with various types of overcurrent protection schemes, including fully rated systems, series rated systems, and selectively coordinated systems. Fully rated systems are designed to handle the maximum available fault current at every point in the system. Series rated systems use a combination of overcurrent protection devices with different interrupting ratings to achieve the desired level of protection. Selectively coordinated systems are designed to ensure that only the overcurrent protection device closest to the fault trips, minimizing the disruption to the rest of the electrical system. Coordination studies are performed to determine the appropriate settings for the overcurrent protection devices in a selectively coordinated system. These studies involve analyzing the time current characteristics of the overcurrent protection devices and adjusting the settings to ensure that they operate in the desired sequence. Maintenance and testing of overcurrent protection devices are essential for ensuring that they will function properly when needed. Circuit breakers should be periodically inspected and tested to verify that they are tripping properly. Fuses should be replaced when they blow. Ground fault circuit interrupters should be tested monthly to verify that they are functioning correctly. Understanding available fault current and overcurrent protection is essential for ensuring the safety and reliability of electrical systems. By properly calculating available fault current, selecting appropriate overcurrent protection devices, and maintaining and testing these devices, you can protect your electrical system from damage and prevent potential safety hazards. There are several specific scenarios and considerations that are relevant to understanding the differences between fully rated and series rated systems, as well as the implications for installers. For example, in a large commercial building with multiple floors and a complex electrical distribution system, the available fault current at various points throughout the building can vary significantly. The available fault current will be highest at the service entrance, where the building connects to the utility power source, and will decrease as you move further away from the service entrance due to the impedance of the conductors, transformers, and other equipment. An installer working on a branch circuit on an upper floor of the building may encounter a significantly lower available fault current than an installer working on the main service panel in the basement. This means that the installer on the upper floor may be able to use lower rated and less expensive overcurrent protection devices than the installer in the basement. However, the installer on the upper floor must also ensure that the overcurrent protection devices are properly coordinated with the upstream devices to ensure that only the device closest to the fault trips, minimizing the disruption to the rest of the electrical system. In an industrial facility with heavy machinery and equipment, the available fault current can be very high due to the large electrical loads and the potential for short circuits. In such a facility, a fully rated system may be the most appropriate choice to ensure that all of the equipment is adequately protected against fault currents. A fully rated system would require the use of high interrupting capacity circuit breakers and fuses throughout the facility, which can be more expensive than a series rated system. However, the increased cost may be justified by the increased level of protection and reliability. In a residential setting, the available fault current is typically lower than in commercial or industrial settings. However, it is still important to properly calculate the available fault current and select appropriate overcurrent protection devices. In a series-rated system, the installer must carefully select and coordinate the upstream and downstream overcurrent protection devices to ensure that the upstream devices will trip before the downstream devices are subjected to excessive fault current. This requires a thorough understanding of the time current characteristics of the overcurrent protection devices and the potential fault currents at various points in the system. Another consideration for installers is the labeling requirements for electrical equipment. The National Electrical Code requires that electrical equipment be labeled with the available fault current at the service entrance. This information is essential for ensuring that the electrical system is properly protected against fault currents. The installer must also ensure that the overcurrent protection devices are properly labeled with their interrupting ratings. This information is important for maintenance personnel and for future modifications to the electrical system. Installers should also be aware of the potential for arc flash hazards when working on electrical systems with high available fault currents. Arc flash is a dangerous phenomenon that can occur when a short circuit creates an explosive release of energy. Arc flash can cause severe burns, blindness, and even death. Installers should wear appropriate personal protective equipment, or PPE, such as arc-rated clothing, gloves, and face shields, when working on electrical systems with high available fault currents. They should also follow safe work practices to minimize the risk of arc flash.